I have a few slides to kind of introduce the topic. And then in the GitHub folder, you will find both these slides, or a slightly older version of them, and then the actual material that we will run in a Markdown file. So just to explain a little bit what I'm talking about, let me take maybe 10 minutes of time to go through these slides. So I've presented some of this work before at JuliaCon and other venues. So you'll be able to recover the information. I'm just going to skip very quickly over today, but the idea of this, digital twin for ocean robots framework is to bring together observations and models in order to enable mutual benefits, such as data assimilation, where you might also be thinking about learning parameters in a model from observations. And then in reverse, we want to have the ability to plan and hopefully optimally plan deployments of observations and observational strategies. So the sort of thing that I'm talking about is not new. In a way, this is the sort of things we've been doing for a long time. This is an example where, from a paper in 2015, we were doing the learning of mixing parameters in the ocean from Argo data. The example that I picked on the left, you can read in the paper, is an out-of-sample verification, in the sense that the mixing parameters for the ocean model were inferred or optimized according to physical observations over a 20-year period. And then this is what happens when I use them and I demonstrate how they improve simulations over 500 years and for biochemistry. So what you see here in the bottom panel is the currently observed zonal mean oxygen concentration. At the top is with the unoptimized model parameters after this 500-year simulation, and in the middle is the result when it has been optimized. The physics has been optimized. And you should see that it's a significant improvement. It's an improvement that relates to what is called the AMOC as well. So in the top panel, there is virtually no AMOC left. In the middle panel, there is a realistic ocean state. And that's an important topic for various reasons, but in particular because the AMOC is something that has a strong impact on the climate in Europe. And so you've heard of those scenarios where the Gulf Stream is modified, and then that would affect us, right? So another very directly related example is a new program that's been spun off, and another reason why I'm continuing this work, and the digital twin for ocean robots framework is going to be applied to this. There is a UK program called Forecasting Tipping Points that's ongoing, and we've been funded with some of my colleagues here as part of that to deploy a new sets of observation to measure mixing and hopefully enable a forecasting of whether or not this AMOC system might shut down, and then the climate in Europe might be affected. So this is one example where the framework that I'm describing is applied directly. You can read more about the framework itself. There is several presentations, as I've said. It includes a lineup of models, a lineup of observations. I have already shown you a little bit about the model lineup before. So I'm going to focus mostly today in this session on the observational side. The QR code should lead you to the JuliaCon conference paper. And then you will find more information on GitHub, in other publications, and of course in the documentations of the packages. At this point, I'm just going to give you a little bit of updates from 2025, so the stuff that you won't find in what I just said. So some of the things I've done this year as part of this. So I've designed a method, a very simple method to do a geospatial mapping of these sparse observational data sets that we have, and that's built been built in. So it's similar to what Alex was describing, but quite a bit simpler. Essentially, you just do sample averaging over boxes. That's it. I've added a couple of data streams, one for what's called XBTs. These are simple probes that measure temperature that you kind of drop in the ocean and then they just fall and they measure temperature. It's one of those data sets that dates back to the 80s, and so it's a very climate relevant data set. And then the one that's on my left, your right, over there, it was called the continuous plankton recorder. So I picked that example here to illustrate because it's a kind of a very beautiful technology. This is a purely mechanical device, right? It has been used to create a time series since the 1950s of biological information about plankton. And it's kind of an amazing thing that's been designed. It's essentially you put a stream of water through the device, and there is two pieces of silk that kind of capture the marine ecosystems in it. And so this is, there is no electronics whatsoever in this. So taking this new technology, now you can access it in Julia. Fun, right? Old meets new. Another recent development has been the introduction of Parquet by one of my colleagues. And then I've implemented this in Julia. So we now have an example where we have the Argo database. So this whole set of observations from the buoys that we have talked about a couple times already. Parquet is a quite interesting format for this because it enables much speedier exploration of an entire database and kind of slicing to it. It's a bit like ZAR, but for tabular data. And then I've done some integration with regard to polygons. So I'll illustrate some of this with the CPR dataset in a sec. On the models, a few more additions. I will highlight that ocean shenanigans is now an extension of climate models, as opposed to, it was not quite as integrated before. So now it works as an extension. In Julia, that means you install the two packages and magically they work together. I've created an array of polygon structure that is sort of building on the JuliaEO work, maybe suboptimally. We will discuss that further later, maybe. I built a bunch of Mackie recipes for the various things and added support for this Nemo grid. So this is what's depicted over there. This is essentially the same grid that Simone was telling you about, more or less, or at least the topology of it is the same. And so the tricky part here is to handle the kind of connecting pieces, right? How do you go from the far left to the other side, which is the other side of the Earth? And at the pole, how do you do that? And another grid that I've integrated is from the satellite data set, kind of reanalysis of ocean current product called Oscar. So here is the lineup of observations today in Ocean Robots, which is one of the core packages of this. We're going to look at a couple of examples, and I've already mentioned some, so I'm not going to go in too much detail. You can find this online. This is the surface drifter dataset example that is in the talk. We will run this in a sec. Drifters GL is the modeling counterpart to that. That is, how do you simulate pathways in the ocean if you know the ocean currents? We will run this in a sec. And so taking ocean robots and drifters together, you make this pairing that I was describing as a digital twin, where on the left you have, on the right, you have the physical twin, meaning the actual observations. On the left, you have the simulated, the emulator, if you'd like, the model we are trying to train. And in this case, this is an extremely basic case. You see that it's much more laminar, right, than what's in the observations. And that is because all I did was take the observation, make a sample mean on a grid that becomes my model, and then I put that as an input to the ODE solver that computes the trajectories. But nevertheless, with this very simple emulator, we're already capturing the basic flow pattern. That is what is called the loop current. This is the Gulf of Mexico, and feeding into the Gulf Stream. So we're going to look at this in a second in practice. We'll also look at this one. This is the Argo profilers that I've been telling you about. So the idea behind, or one of the core idea behind this Ocean Robots package is to provide an interface to this data set that is as simple as what you see at the top. So a read command and a plot command that download things on the fly if needed. This is the climate models GL's documentation. An example that we won't run today, but gives you low-dimensional emulators, so the fastest climate models you can run, really. And this is a Python one. And then there's a functionality also to query the CMIP6 archive, so the big archive of climate model output generated by the IPCC. At the end of this presentation, if you want to continue, here is one thing I would suggest you can do. Generate Argo observations in the future. How do you do that? You take real observations and you add a climate perturbation to them. And so this will involve both ocean robots and climate models. At this point, I'm going to go in the actual demo part of this. So if you go to the JuliaEO website and you go to the repository, you will find the notebook, meaning in this case, just a markdown file. Here, and it's this guy. All right. So this is the examples that I propose that you try out. You can pick whichever, but I'll start from the top. And so what we're going to do is, in fact, I'm going to go away from this a bit. I can use this version. I think you see a little better this way, right? All right. Okay, so I've already done this part, but let me show you how that works out. So we are in a given folder, right? And we're going to do Julia. We're going to do import package and package activate. So this is something that most of you that are proficient at Julia know very well, but this is creating a local environment locally. You can create a temporary environment if you prefer. Anybody has a question on that part? That seems familiar, right? Maybe, maybe not. Okay, so I'll proceed. If you have questions, do not hesitate to interrupt, please. So let's go back here. So now we have our little environment. We're just going to copy and paste these two commands. And I'm going to do it this way. You don't have to do the beginning and end, but just a slightly nicer way to containerize things. So what this does, I've run this before. So if you run this yourself, like Simone has shown before, there might be some latency due to downloading packages and compiling them and so on and so forth. None of these are particularly big, right? So this is mesh arrays shapefile, which is one of the packages from the JuliaGeo organization, I believe. And data depths is for data dependencies. There's this one comment that within mesh arrays, you provide the name, like a code name, and mesh arrays goes out and downloads the data set and reads it into this little data structure that I've mentioned before, called a poly array. So this is an array of polygons in the way that I kind of like it. Maybe not the most standard way at this point. I want to kind of revisit that, but this is going to be for visualization, essentially. Yeah, go ahead.
I lost a second. Where can I find this notebook? Because I don't seem to find it in
It should be. On the day forward, you should have a markdown file.
Markdown.
Yeah, it's a notebook-ish. No, you can, but it's you just copy and paste it. Oh. I didn't quite create a notebook proper. Any other question? No? All good? All right. So this is essentially to get some context when we are going to be plotting things. The next code block in this I'm going to call it a notebook, right? But markdown file, is the surface drifter dataset. So this is now going to look like this. We have two packages here that are kicking in, Ocean Robots and Kairomaki for plotting. Ocean Robots is the one that handles all of the data sets. For what I'm showing to work, in fact, you probably need also the data depth dependency extension that was activated before. Is that right? No, I think data depth is an external dependency of Ocean Robots. So what's happening here is that in the background there is a little bit of compilation going on of packages. Once that's done, the read command does a little more than read. It downloads datasets if needed. So this I've run this one before. It should skip the download for me. It might go slower for you. And given the Wi-Fi here, I cannot guarantee how speedy this is. But this is a fairly small set of files. So it should not take too long. You see here that I have a set of extensions that are getting activated, precompiled. So Ocean Robots has direct dependencies, but it has also these extensions that pair up and then help you do things. And so here you're seeing the result of the workflow. So the read command gets a name of a data structure that sort of tells it what to do. This is multiple dispatch. That's one of the things that is used everywhere in Julia that you already have heard about. And there is an ID. Here I'm just saying grab the first one, the first drifter. The read command, after downloading this file, puts it in a data structure that, in this case, you're going to recognize to be, oops, I guess the display is not great. Something I can improve. It's of the type surface drifter, sorry, and it gives you the ID. The data is somewhere embedded in there, and there should be a nice method to show you the data structure, but I'm not going to call that pretty at this point. And then the plot command, right, knows what to do with this data structure. And so that's how you end up with a very simple way to visualize immediately the data. So the philosophy behind all of this is that for teaching, for communication, but even for exploring the data for science purposes, you want to have the minimal amount of commands and kind of pain points. And so this is a very sort of quick and simple entry point to these data sets. The plots are, in each case, customized to this data set. So here you're looking at the time series of the velocity of this device that's been drifting in the ocean. These are the middle panel. That is an observing system that also records temperature. And so you have this shown in the bottom plot. And then I added a couple of things. So the actual trajectory of the surface drifter, right, this buoy that follows the ocean currents. And then a scatter plot of the velocities. Something you might want to learn. The scattering of this, you might think of, in some cases, as a stochastic element to the trajectories. All right, so this was my examples for the surface drifters. Anybody have a question on that one? Or a comment? Or no? All right, excellent. Keep going. We're going to do an Argo float now. So same idea. So now we are going to query the Argo database and download just one float and plot it. Same idea, same workflow, exactly what I described before happened right here as well. So it will also download a little bit of data if you haven't downloaded this float before. The plots are different, right? Because this is a different observing system. These Argo floats, what they do is they drift in the ocean at a given depth, typically 1,000 meters. And every 10 days, they go down to 2,000 and back to the surface, observing temperature and salinity, transmit their data via satellite, and then we recover them on land and we use them in our ocean analysis. right? This is a sort of maybe one of the biggest, most important system of observation for climate change. This has really become the backbone of climate science in many ways. That's one data set that I use pretty much constantly. So the plotting here shows in the bottom panel the time series as a function of depth and time of temperature and salinity. I might have interpolated them to standard levels automatically. Depends, there's different options. And then the top right for you is the trajectory of this float with, in color, the time since launch. So you see that this guy actually has been at sea for almost 4 years. They don't all last this long, but it's kind of typical. And then on the right is just a quick estimation of the speed at which they drifted. And that is not as accurate as for the surface drifters because we only record one ping every 10 days. But this is just looking at what's happened. For Argo, I have in fact a more elaborate package that you can look at called argodata.jl. I'm not going to get into this, but it contains a few more capabilities, and especially the geospatial mapping, which will move elsewhere sometimes. Alrighty. So, I think these are my 2 examples for now on data sets that we will do at the command line. But if you want to look at more, as I said, there is a whole suite of them. And in general, in my documentations, you will also find, do you have a question?
Do you have in that article, do you have the possibility to search all articles, because it's selected by a metric? And the region and area and time, all of them.
Yes. What I'll show you with the continuous plankton recorder is that. So it's sort of the same idea. In Ocean Robots, there should be a query method for each of the data sets to sort of get the list of what's out there. And you can start exploring from there. For the selection by region, that's where I'm using polygons, for example. So I'm going to show you an example right now, which is, I guess, sorry, 1 second. Oh, okay, never mind. So this is the Ocean Robots documentation. The list of supported data sets is here. So you'll see that indeed there's the surface drifters, the Argo profilers, XBTs, NOAA buoys, glider data sets, and mooring data sets. So that's, if you're not in oceanography, that might not ring a bell, but these are a bunch of the most important ways that we observe the oceans. And one specific one that's also useful is this OceanOps interface. So OceanOps is, to your question, a service that monitors and lets you know what's being observed at any given time. So it kind of centralizes all of the data collection at the level of UNESCO, essentially. And it's one way to know, well, what's happening now in terms of, is there a cruise at sea? How many Argo floats are out there, and so on and so forth. If I go back to this page, there's the notebooks, and this is why I opened this web page. I wanted to show you what we're about to run, which is, I have lost this one, here. So here is my example for the continuous plankton recorder, and I'm going to start it and then explain what this is. So in this example, going back to my notebook, I decided to illustrate how you use Pluto with this. So in any of the Pluto notebooks that I've included, you start with this Pluto run pluto.run parenthesis command. And then you have this interface, right? That opens in your web browser. The idea is that when you go in, you grab a URL, and this is the one I grabbed from the documentations of Ocean Robots before. Come back here, bang, bang. So this has the advantage, as we've discussed earlier in the weeks, that these notebooks embed the environment, so the project toml and the manifest toml. And this is why they are essentially self-contained. You just need to know the URL or have the file on your machine, and you're basically done. There is a little bit of a progress bar at the top. See it better there, right? That's going to take a minute. I've pre-run it, so all right, great. Faster than I thought. So again, this is downloading a bit of data and so on and so forth. But it illustrates the subsetting with polygons. This is a data set that's relatively small, so it comes, I think, in one CSV file. But the idea is that then you can explore it, and so this is what I did here. I don't know what this does. Oh, okay. Yeah, this is a plot that sort of shows the frequency of the observations. So you're kind of looking at the interactivity of Pluto. And then the selection by polygons is here. So this is using directly, in this case, the geometry ops package, which handles polygons, or geometry data in general, and has a function that just, you give it a bunch of points and a polygon, and it tells you whether it's inside or outside. So this is how this plot is done. And that method applies, generally speaking, to anything that you can put in a, if you can provide just the longitude and latitude, you're good to go. I have implemented on top of it a bit of a wrapper to work with my polygon array format, so that there's a bit more integration with all of my things. Because otherwise I was struggling with different kind of different file formats. So polygons come in different flavors. There's, for example, GeoJSON and shapefiles, and they are sort of differently structured, slightly differently read in memory by the Julia packages. So I've just tried to make this a little more user-proof. Let's put it this way. Was that good enough as an answer on that? Cool. Yeah, the geometry operations framework is something that I started to learn about from some of the people here last year, and I have to say, I'm a fan. I think I gave myself another 10 minutes on this, so I'm going to keep going to the next example. I wanted to show you the Drifters GL package. So this is now, I'm going to run this right away. This is one of those, so to quit Pluto, by the way, just Control-C and you're done. So this is going to demonstrate something different, which is how do you simulate the kind of observations that we are collecting. It's taken from here, the documentation of Drifters GL. So this is, I didn't make anything new. You'll find the exact same one online. This provides essentially the flow fields that are then wrapped into this flow fields data structure. Individuals is the data structure that is going to correspond to a set of initial positions that then are going to be advected by the flow field. And this operation takes place here. In this instance, we're doing a number of time steps. So this is just a loop. And things get recorded in this little variable here. So that by the end, you get a data frame, which I believe contains positions of the generated trajectories along time. And so once you plot it, it's going to generate this. Again, sort of like before, but a little bit less pre-canned is the plotting. So this is all that's taking place in this case. I'm just going to go and double check that this indeed ran. So if I show you what's inside of this data structure, it does have positions expressed in X and Y. Here this corresponds to longitude and latitude, time, and there's an ID for each of the trajectories. So this is just a standard data frame, meaning you can start applying data frames being a tabular format. That implies that you can start sorting and group by and all of those nice functions that let you explore the data set. The next phase is we're going to plot it. I think still probably is in memory, yeah. So this is the next code block that is in the notebook /markdown file. We are now using mesh arrays, GeoJSON, there we go, and data depths, sort of same as before, but not a shapefile. In this case, a GeoJSON dataset is used for the context, the coastline. And what else? So the plotting is kind of pre-canned, but it does have some options. So this is just to show you can set limits and add the polygons or not. One of the functionalities that we are using here is we're wrapping the output of the particle trajectory simulation in a new data structure called Drifter's dataset. And that, again, is such that multiple dispatch is used in the plotting, and we don't have to worry about providing all of those options. They kind of carried through and are handled internally by Julia. All right, I think I have another 4 minutes to show you the last one. The last one is a simple example of climate models GL. This is like the simplest one you'll find in the documentation. Oops. This runs a climate model that really shouldn't maybe be called that, but is a simple random walk process in 2 dimensions. So it's going to generate a trajectory that just scatters. It represents a diffusive process in some way. And so this has completed. The reason I use this example is it's the fastest, and it allows me to still demonstrate the data structure. This is what happens when I also run oceanigans or the eco-ocean analysis, the MHGCM or whatever through this. That is, it goes through a set of 3 methods. One is called setup, the second one build, and the third one launch. Depending on what you do, these things are different, right? If you're doing a Fortran model, well, you're building in a certain way. If you're using Julia, then kind of it's built along on the fly. So on and so forth, but abstracting this away means that we now have a unified interface. And this is equivalent to if I was showing you the MHGCM or shenanigans. There's a data structure called an abstract climate model, I believe. I'm just going to check that. Sorry, it's called a model config in this case. And what happens after that, when you call the run function, so run is the combination of those 3 other methods. So it's a shorthand for set it up, build it, launch it. At the end, everything is also put in a little folder that's been created for you, which is indicated here that you can take a look at directly this way. Right. So now this CSV file that you're looking at in my terminal window, that is the output of this random walk. We could read it. I'm just going to go and give you the visualization this way, right? So these are all of the positions of this random walk process. In another model, the output might be very different. It might be a bunch of netcdf files. It might be plots. It might be whatever. But so that's my workflow for this sort of things. And there is another thing I want to demonstrate, which is this. So you can iterate on these model runs. When you do that, you want to keep track sometimes of, I want to keep track of the sequence of what I do. Like, okay, I'm going to change the number of parameters, I'm going to rerun. Then I'm going to maybe change the strength of the flow fields or whatever. I want to keep track of all of this. And so that's why I have built into this a Git record of everything that gets changed along the way. And so this is what you're looking at here. So this is the record of what's happened in this model simulation. The case of, the case of more complex models is the same. There is a suite of different models in here. Right, so everything that I've just explained to you is in the documentation. So if in case that went a little quick, you will find there as well the list of the models that are currently supported. Some of them, I call them running models, and others replay. Replay would be, okay, I've already run the model. I don't need to rerun it every time. I'm just going to read the result from the file, right? And then I'm going to build something else on top. The one thing I will show you is the Ocean Higgins example, because I think it sort of is the way that I'm going to proceed when it comes to building more complex models. So I have two things in there. In the SRC folder is essentially everything that does not require actually having Ocean Higgins used. In the extension is everything where I need to actually have Ocean Higgins. And so the point is that I don't need to include as dependency every model that I want to build into this framework. I just need to build them as extensions for the minimum amount of kind of pain and overhead, so that I don't have to compile Ocean Higgins every time I use climate models, for example, right? And I'm just taking Ocean Higgins as an example, but it would be, I'm just taking it as an example because it's the best model out there, right? Let's put it this way. And so then what is in the extension resembles very much what is in the documentation of Ocean Higgins, just kind of pre-canned and curated. That's my goal, is to have available to me in the fastest, simplest way a certain subset of the simulations that Ocean Higgins or Climate Ocean and other models can generate. And so just little functions that sort of build this complexity, or this maybe apparent complexity of using Ocean Higgins, and reduces it to the user for building and for setting it up and so on. So it's nothing that I invented, just organized differently. So that at the end, the way that I just ran the random walk model, I run Ocean Higgins exactly the same way. Just run it. I don't want to hear more. And then, of course, there is possibilities to provide runtime parameters. So again, Ocean Higgins might have a gazillion options if you really go through it that you can parameterize. My experience with models and model users is that often a lot of people want something that's a bit more constrained. Things that they know they can trust is going to do a previous result the same way, and then start from that. And so that's the spirit here, to sort of restrict a little bit the range of possibilities to a certain set of users for a certain set of applications. So it's complementary, I think, to the approach that Simone is taking. I think that's all that I have for today, and I'm also out of time. So thank you very much. Don't hesitate to ask questions now if we can take another couple minutes, but I think we have a break, don't we not? I don't have the agenda in front of me. Here. Where are we? If you have any quick questions, I'm happy to take them. I don't want to prevent people from going to the break or the next speaker to start. Where are we? We are here in... Yes, Andre. Sorry, I encroached on your time a little bit.
No worries.
Thank you.